Okay, so we're now up to lesson 128. This is a pretty tough lesson here, and I want to pick out particularly the bit on combination circuits, and then I'll just touch briefly on multi-wire branch circuits as well. So most of our time here we're going to spend on combination circuits. So I'll pull one out of the textbook, one of the examples they use, and what you see here is a combination circuit. So what does that mean? It means it has elements that are connected in series, and it has elements that are connected in parallel. So kind of the trick, and the first thing we want to do is let's just sort of identify what elements are connected in which ways. So here we kind of see these we have four elements. Here's one element, here's the second, the third, and the fourth. So if we look at sort of elements 1 and 2, as I'm calling them here, these are connected in series with one another, right? And we can sort of see that in a moment here, but elements 3 and 4 are connected in the same way. So we can sort of watch electron flow. We have one parallel path right here that we're seeing. Then we have a second parallel path through this set over here. Okay, so just another way to sort of reiterate that. If I take that away, I just have a simple series circuit here with two elements. Same thing if I just look at this side. So you can see again, we just have two simply connected series circuits, right, with two elements each. But then we go ahead and sort of connect them in these two series connected sections in parallel with one another, right? So this group of elements is connected in parallel with this group of elements. Okay. So let's just look at this first little section of a series circuit, right? And I'm not going to run you through all the math and everything, but here's a table kind of solving for all these values. So your trick here, again, is group these things up in their simpler elements and solve them as you would if it was just a series or just a parallel circuit. So in this case, we just have a simple series circuit. So again, I won't drag you through the math, but if we were to solve for all the values, this is what we should get. And we can do the same thing for this second section of series circuit over here. And they mentioned in your textbook these all have equally rated values, so naturally they're going to look exactly the same. So really what we've done here is we've just solved for two series circuits here at this point, right? So let's bring everything back into play here. So that's good. We know all the values for this little section here. We know all the values for this section here. So what do we want to do with that? Well, sort of the next trick in my mind, let's go ahead and just imagine that this was only one element now. So once we've solved these total values here, just consider this to be one element. Instead of two elements in series, it's now just one element as long as we apply the total column values here. So again, we had sort of a two element series section here, but let's just again imagine that it looked like this to begin with, right? So now if we use these total columns, so let's actually bring up a new blank table here. So now if we look at it this way, we just have two elements that are connected in parallel. Okay, because again, we're going to use our total values here and our total values there. So I'm calling this load 1/2 and load 3/4 because again, originally this was two loads. But if we combine that, we use these values in the total column, we can now solve this as if it were simply a parallel circuit calculation. And of course, I'm not going to drag you through the math here, but if we used our parallel circuit rules, we would get this as our total value for the entire circuit. So again, kind of the trick on any parallel circuit calculation is break it down into its more simple parts. So find a section that is simply series connected or that is simply parallel connected. Solve for that section as best as you can. And again, the trick is going to be find your resistance first. You should theoretically be able to go through the entire circuit finding resistance of everything. Once you have that, the rest will start to fall into place. But anyway, with these combination circuits, listen, it's tough stuff. It's not easy. Stick with it. Don't get discouraged, and please reach out if you want to maybe see some more examples or get a little more practice in one way, shape, or another. But this is not easy stuff, and it's not stuff you really have to do every day. But it really does give you a really good, deep understanding of sort of electrical theory and how all this works in the grand scheme. So one last little piece here, I just want to focus on a multi-wire branch circuit. So they mentioned that, I don't know if they do the best job explaining what that is in the textbook, but One way you might be able to think of that is a shared neutral circuit. Okay, so something that used to be common, not so much anymore. If we have two circuits, okay, maybe they're at the same place. So think of your small appliance branch circuit in a kitchen. You need two circuits in a relatively close space. Maybe you're just going to run one 3-wire. You have a black, which is one hot. You're going to have a red, which is another hot. And then let's share our neutral between the two. Now you can do that, and there's certain things you need to follow and ways you have to do that. But the reason that works is if we have one hot on, let's say, A phase, and we have another hot on B phase, as long as those two hots are not on the same phase, their neutral current will actually cancel out. So another way, what does the neutral do? It carries the unbalanced load. So another way to look at that, if this were 12 amps and this were 10 amps, these 10 amps would cancel out 10 of these amps, but there would still be 2 left. They would be imbalanced by 2 amps. That neutral would have to carry those 2 amps back. If they're totally balanced, there theoretically and literally will be no current on your neutral in this case. So 10 amps here, 10 amps here leaves me with 0 amps on my neutral. And again, this is, I'm not sure if you find this helpful or not, but for me it really brought it into perspective. So if that has 0 amps, in this exact scenario, do we even need this neutral? And you might be kind of thinking, well, how's that going to work without it? Well, I might say, let's imagine that as if it were a series connected circuit now. And if we think back to our series circuit math problems we did, if I have 2 equally rated loads, they will each get an equal amount of voltage, right? Because voltage is additive on a series circuit. So if these are equally rated, and they must be if they're both 10 amps, right? Each of these is going to get the same proportion of our available 240. In this case, again, on equally rated loads, I can divide my voltage by the number of loads on a series circuit. They'll each get 120. So they're getting exactly what they need. There's no current on the neutral. And in fact, in this case, it's not even really doing anything. So in this sort of perfect scenario, theoretically, we've really constructed a series circuit. Now, we wouldn't wire things like this because, again, if somebody put a different light bulb in here, plug something else in, now we're not in balance. And that's going to create the scenario in your textbook where you lose a neutral, everything's out of whack. And, but again, it sort of all comes back from a theory point of view in my mind of that deeper, better understanding. But, again, this is a tough chapter, a ton of technical info in here. Please, don't be shy to reach out if you need a little extra help, and I'll see what I can get up here for you.